Okay, got a lot of questions this morning. So we're going to start with the ones I got emailed. So first one's going to be coming from question 30 on the organic connect homework. Based on the question I got, I'm guessing a lot of this really just kind of boils down to how it's like just the software being finicky, but I'll go ahead and work through the problem. So the question here, you have this one butanol with PBr3. Draw the structure. PBr3 here is a very stereoselective reagent, very good at substituting primary alcohols to what they're supposed to, what you want to be, what you want to substitute for, which is bromination in this case. So the nice thing about this mechanism is that we're not going to like get carbocation rearrangement. This is going to be a pretty fast, efficient reaction. So in terms of the mechanism, we've got positive attacking negative. Wait a minute, I'm trying to remember. So we should have positive attacking negative, and in terms of the ion that comes off, going off of memory here, this is why the notes are really good. If I do this from memory, I probably should actually just go ahead and open up the notes because the notes will talk about this mechanism much, much better. Hold on, let me look up the notes. I don't actually know this mechanism off the top of my head. Gotcha. All right, so step 3 was where student was saying they were having issues. So we're going to have the bromide attack the carbon. This is going to break the carbon-oxygen bond, and should be it. Yep. So if you're having issues with this one, remember, keep in mind the bromine is displacing this, so it's going to attack the carbon, break the carbon-oxygen bond, and that's going to give you this HOPBr2, which in principle can continue to react, get rid of all the bromines that are on to give you the phosphorus hydroxide. That would be my best guess, is that the attack was drawn to the oxygen or just drawn slightly off center. Oh, have I had this on the desk? Had this on me the whole time? Okay, so in terms of the actual mechanism, it's bromine attacking the carbon, that'll break the carbon-oxygen bond, and then you get this HOPBr3 structure. All right, so there's that question. A few more, and then I'll get to the questions I got asked in the chat. 28, 29, 36, 38, and 48. Thionyl chloride. Thionyl chloride is going to take kind of the same approach. So let me draw it up on, bring it up here. So thionyl chloride is going to pretty much follow a very analogous reaction with PBr3. So we're going to break the sulfur-chlorine bond by having the oxygen attack the sulfur. Now, fun fact, the thionyl chloride reaction, I think, is actually debated, or no, it's the tosyl chloride, the TSCl. It's kind of debated how that reaction actually works. So you're going to have, definitely with newer textbooks, you're going to find things that really contradict what's in old books like Carey. The truth is, some of these mechanisms are not well understood. In this case, our pyridine is just acting as a nucleophile. It's big. So it's going to do more of an elimination reaction. In this case, it's eliminating the hydrogen from the structure. And we're going to get this short-lived thionyl complex. It takes forever to draw. But basically, this creates a really stable group that's good for leaving. And then finally, you get the elimination reaction from the chlorine, or I'm sorry, the substitution reaction. The chlorine here is a small ion. Does a really good job of slipping in. It's not basic at all, so it can't do any type of elimination reaction. All right, hold on. All right. Oh, stop it. We've got an extra step here that we've got to break. Chlorine Chloride attacks the carbon, breaks the carbon-oxygen bond. This attacks the salt, bonds to the sulfur, and gets rid of the other chloride here. And so we end up producing the chloride ion. What? Oh. Let me bring up the notes really quick for this last step. Wow, that's so weird. It's like they're missing an atom in their own reaction. So the HOSCl2 is the correct product. Really? Show me the answer. I don't believe you. Okay. This is annoying. Okay. So for question 28, I see the problem. There's a bit of a nuance to writing out the answer in this one. So for this one, you get the chloride attacking the carbon. And instead of drawing this bond here from the oxygen and then from the oxygen back to the sulfur, you're actually just going to make it basically leapfrog over the oxygen and then break the oxygen or sulfur chlorine bond. So when it comes to drawing this one, it's actually just a weird little nitpick here. Instead of drawing the reaction mechanism arrow from the bond to the oxygen and from the oxygen back to the sulfur, they just want you to draw the bond kicking all the way over. And then is the chloride and the SO2. So yeah, that's just kind of a really obnoxious little nuance about the problem. So let's take a look at 29 while we're here. You got SOCl2 with pyridine, and you want to predict the minor product of the following reaction, then draw a stepwise mechanism for the formation of the major product. So your minor product here is going to be basically the inverted stereochemistry. So thionyl chloride, it's another one that's kind of debated what the mechanism actually is. And the reason it's kind of debated is it's supposed to go through an SN2 pathway with the chlorine, but every now and then it will go through an SN1 pathway. You create this carbocation. And because you get this carbocation, you can actually get both products, the R and the S forms. So your minor product here is the one where you get the OH substituting the OH, and you getting, this looks like the R formation, whereas you have the S up here. Generally speaking, thionyl chloride, SOCl2, is going to give you this major product. That's pretty much going to be all you recover, but you will occasionally acquire some of the SN1 product. Now, writing out the mechanism, it's going to go back to what you did before on the previous problem. We're going to have the oxygen attack the sulfur, and we're going to displace the chlorine. And our final product here. And you're going to have to include every piece of stereochemistry with this as well. Pyridine is going to abstract your hydrogen. And I am not drawing this whole bit of nonsense. Now, in terms of the final structure, this is probably going to be another one where it wants you to leapfrog that bond. So you're going to attack the carbon, carry that bond over the oxygen to the other bond, break the chloride. This is how you get that inversion, is that you're going through an SN2 pathway and you get the chloride and the SO2. So yeah, you just got to do the leapfrog for that double bond. Uh, 36, 38, and 48. So when students ask me, like, do I think the mechanism, like, what's more important to memorize, the mechanism or the overall? This is why I say the overall. Some of these mechanisms really are kind of debatable. Like, SOCl2 should do that, but every now and then the oxygen-carbon bond will break and you end up getting a SN1 pathway. So NaNH2, this is going to undergo substitution. This is very much under basic conditions. You're under aprotic, and you're definitely not going to get 2, 4. And then your inorganic product is just the NaOH. Oh, really? Oh, oops. Probably would also help if I put the camera on here too. On the desktop. Okay, so the reaction here. Actually, this NaNH2 is going to abstract a hydrogen from the alcohol. I do need to correct that in the packets. And that's a mistake on my end. I don't think you draw the bond in there. So your organic product here is the alkoxide. And then your inorganic product here is ammonia, NH3. And I do need to correct this in the packets. I think the packets show the NH2 doing a substitution reaction. All right, 38. Sodium bromide and sulfuric acid. You are going to get carbocation rearrangement here because you're underneath sulfuric conditions. So this is going to be a protic solvent because you have the H2SO4. So my guess here with the bromine doing a substitution is that you're going to get a secondary bromide. Does it think you're actually doing a primary substitution? Of course. I think I've sent them complaints about this question before. Okay, so apparently it thinks you're doing an SN2 mechanism here with the 1. Again, this is the debate between whether it's SN1, SN2 based in our conditions. This H2SO4 here would lead me to believe that it's protic solvent. I thought it was SN1. It's actually SN2. The big tip off here is that if it was SN2, it should have made you do both the R and the S products. And then I think that's it. 48. Oh boy. So with this one, it's actually not as hard as you're probably thinking it is for 48. So you've got this HCl and you can pop off the OH, and the question is whether or not the Cl attacks from the top or the bottom. So when we build this structure, and it is going to nitpick you, you do need to have it this methyl group up, or it's going to create problems for you. We create a carbocation on this carbon. We can either have the chlorine be axial or equatorial. So if we attack from the carbocation from the top, we're going to get an axial chloride. And if we have an attack from the bottom, our methyl group will get pushed up and our chloride will be pushed down. We'll be in the equatorial position. Now, this will occur through SN axial, and chlorine is axial, chlorine is equatorial. It doesn't matter if this proceeds through SN1, SN2. This is a tertiary carbocation when it gets formed, so there's no reason to believe that it's not going to stay on that carbon. So the two stereoisomers are definitely, let's see here. So if we look at it, the question is whether or not this is a chiral center or not. I would say it is. And you've got two chiral centers here. You've got, hold on. So let's work it out on the board. So here I've got 1, 2, 3, 4. So as you're I've got the chlorine up, the methyl group down. And on this side, there's an axial pointed down. So the chlorine and the other methyl group are cis to one another. The question is, are these chiral centers? So if I look left and look right, I'd argue there's no chiral centers because there's a mirror plane running down the center of this. So because we have this mirror plane running through the molecule, we don't have chirality. These would be, well, we do have chirality. So if I had the other one, so I have the one where that's equatorial. And so no, this is in fact a chiral molecule because we have these cis to one another versus trans to one another. And the question is, are they mirror images? So if we take mirror images of, so if I look at it from behind the board, this is a mirror image of this. So this makes these enantiomers. Or, sorry, early working this out. So if I take the mirror image of this, so I look at it from behind and I take the mirror image, I'm going to have the methyl group coming out and the chlorine going back. And this is not the mirror image of this, so this makes these diastereomers. Let's see, do I have enough carbons to build this? So I can build one where the chlorine is axial and the one where it's equatorial. And the question is, if I make them face each other, are they mirror images? And the answer is that they're not mirror images of each other, but they are chiral. So these two stereoisomers here, because they are stereoisomers, but they're not mirror images, this makes them diastereomers. The stereoisomers are chiral. It's kind of a weird way to ask this question because they can't be diastereomers and like achiral. Apparently they are chiral, but they are achiral. Oh, it's early in the morning. Okay, so they are achiral. God, I'm confusing myself this morning. They are achiral because this mirror plane, which makes it a meso complex. So these centers, basically they're achiral in the sense that, that they're meso. This is a mirror image of itself. If you were to take a mirror image of this molecule and turn it around, you would end up getting a rotation. What separates these are the cis-trans. So the trans and the cis make them stereoisomers, but they are not chiral stereoisomers. They are stereoisomers because you do have a ring which prevents constitutional isomers from forming. Now, are they formed in equal amounts? And the answer is no. And the reason they're not formed in equal amounts is because we have this axial versus equatorial preference. So your CH3 group is going to be bigger than your chlorine, is going to prefer the equatorial positions. And so what we expect to see is that a majority of this should be the one where the chlorine is in the axial position. All right, now to the chat questions. Hi, can you please go back and go to S1, S1, each one, E1, I understand that it occurs in each, but I'm having difficulty understanding how to pick which reaction. So in terms of elimination versus substitution, elimination is going to be favored for bigger, strong bases. And the ubiquitous answer for what is a strong base are your alkoxides. So any alcohol that has the hydrogen removed, and so basically if you see tert butoxide and isopropoxide, these are eliminations. Substitutions are small, basic, or weakly basic. Now, hydroxide here is going to kind of fall in a weird position It will do both substitution and elimination. I assure you, you're not going to get questions that are that ambiguous. In the lab, we use actually hydroxide to drive elimination, but you can definitely find plenty of examples where it's used for substitution as well. But definitely things that are not basics. Your chlorides, your iodides, your bromides, and to some extent your fluorides, these are going to favor substitutions. Now, E1, E2, SN2, SN1, these kind of follow the same patterns. So your 1 and 2 mechanisms are going to depend on the solvents. And it's kind of misleading, but also the carbon that's being looked at. So to favor a unimolecular mechanism, this is going to be a high dielectric constant protic solvent. For the 2 pathway, it's going to be a low dielectric constant aprotic solvent. Now, there is no like number you look at and go, oh, the dielectric constant's beneath this. This is definitely a 1 or 2 mechanism. It's a spectrum. The reason it is a spectrum is twofold. Dielectric constants are spectrums. They can take any value. The second is that there is just pure practicality associated with this. If your solvent becomes super low dielectric constant, you can't dissolve any of these. They don't dissolve in nonpolar products. So if you look at something like an ether, ether isn't going to dissolve sodium bromide. So you may be trying to drive the SN1 and E1 mechanisms, but because it's such an apolar solvent, such a nonpolar solvent, so aprotic, nothing can dissolve in it. So when we talk about, and at least the book does a good job of saying this, the majority product, we are acknowledging that the other reactions go on. The question is, which way does it go? So if you see an aprotic nonpolar solvent, and if you go to the test one table, if you go to the tables in the lessons folder, there is a list of solvents with properties. If it is nonpolar, aprotic, it is probably driving a bimolecular pathway. Now, for the discussion board, diethyl ether and acetonitrile, look at them and compare them and then make a judgment call. You should get different pathways, as most of you have seen in my responses. So based off look at the context to the problem, what do you think is the difference between the two? What effect is one solvent going to have? What's it going to favor of one versus the other? Now, the other is the carbon. I don't like teaching it this way because this is very misleading. So your unimolecular pathways are usually tertiary and to some extent secondary. For the bimolecular pathways, this is primarily a first degree, or a primary is going to go through an SN2 or an E2. Now, why do I say that this is kind of misleading? We are talking about what reaction dominates. But the thing is that the unimolecular pathway is faster than the bimolecular pathway. So you may be favoring the SN2-E2 mechanism, but because it's so slow and they're both going on, this ends up being your majority product. And so this is just the nastiness and the hard reality of running organic chemistry reactions, is that you're going to get a mixture. And even though you may have put everything in your power to make this an SN2 reaction, because this goes faster, even though this is happening more often, this is going to be the majority product you get. But again, don't try to break this into binary. This is the only thing that's happening with this reaction. Acknowledge that SN1, SN2, E1, E2 are all occurring. The question is, based on the information you're giving, what is most likely to be occurring? So the discussion board last week about elimination versus substitution, that's why this was intentionally eliminated. Because people get into the habit of going, oh, well, first degree only does SN2. No, it does SN1 as well. It's just that this isn't the majority of the reaction that occurs, but it is the fastest that occurs. So if you run this reaction in the lab and you've got both SN1 and SN2 going, even though SN2 may be the dominant mechanism, because the SN1 goes faster, you acquire more of that product. So your solvent here is going to be the bigger one for determining if you're doing SN1, SN2, or E1, E2. Now, in terms of the actual mechanisms themselves, so let's have an alcohol and we need a hydrogen beside it. If we were doing an SN1 pathway, what's going to happen is that we have to break this carbon-oxygen bond to give us a carbocation. Now, if this is a primary carbocation, it's not likely to do much. And because it's not likely to do much, we don't expect this to be the dominant pathway, but this is a tertiary, so there's two R groups hanging off here. We expect this to be the dominant pathway because the carbocation is fairly well stabilized. Now, what happens next is our nucleophile X will go through and it will attack the carbon. When it does this, it can do it from the front or the back because this is tertiary carbon, and we'll get both the R and the S forms of the product. If we go through SN2, we have to have what's called a concerted pathway. So in the concerted pathway, X attacks the carbon. This breaks the bond between the carbon and the leaving group, and we get X attached and our leaving group passing off into space. Now, again, whether or not it's SN1, SN2 depends on two major factors. The biggest factor here being your solvent. If your solvent is terrible at stabilizing carbocations, you're going to prefer this SN2 pathway. But that said, it also depends on the nature of the carbon. So if the carbon is more likely to be, if the carbon is primary, it's probably going to favor an SN2 pathway. If it's a tertiary carbon, it's much more likely to favor a SN1 pathway. Elimination. So the E1 pathway is going to look a lot like the SN1 pathway in that we're going to break the carbon bond first to get this carbocation. Now the question is whether or not X, which is in this case going to have to be a base in order to do elimination, because we need something to attack that hydrogen. If it's small, it's going to turn around and slip and do substitution. If it's a big group, and this is why we say the tert butoxide, because tert butoxide here is going to be so let's say the blue here is our oxygen. Okay, if we have a tert butoxide, it's going to have to basically push up against a ring with this big bulky group. It's not going to want to do it. So this is where we start favoring elimination with bulky groups, is they simply can't get in there to do a substitution. It creates too much strain within the molecule to do a substitution reaction. Now, that said, we also have to have the caveat that we have to have a hydrogen nearby. It has to be an adjacent carbon. And so if we go through the E1 mechanism, we abstract the hydrogen, and the bond comes down around the carbon and forms this carbon-carbon double bond. The E2 pathway is another concerted pathway. So with your concerted pathways, your strong base takes the hydrogen, the bond between the carbon and the hydrogen breaks, comes down, forms a bond between the carbon and carbon, and this carbon breaks its bond between the carbon and the OH group. Or in this case, our OH group, our leaving group. And so in a single step, we end up forming this double bond. All right. So the textbook and online other sites and other YouTube videos explain differently where you can have two reactions such as E1S2, and they drew the two products for both the runs. Again, no reaction occurs purely. So this is why I'm saying the solvent's going to dictate your molecularity. Because if you'll notice, they had the same reagent. So let's say they had F oxide. And they had this molecule here. And they probably said it can do both substitution and elimination, but you should have caught on that they gave it by the same mechanism, SN1 or E1. And the reason being here is that this is not going to really have an impact on whether or not this carbocation is stabilized. Whether or not you go through a bimolecular or unimolecular pathway depends on how stabilized that carbocation is. So that's where it matters what your leaving group is, and it matters how well your solvent can stabilize it. So again, this doesn't have any effect on the formation of the carbocation formed here. So if we can go through a carbocation, this is what we're going to form. Is we're going to take this chloride and we're going to open it up. And if this is stable underneath reacting conditions, so this is going to be low temperature, low dielectric if you want the carbocation to be stabilized, it's high temperature because it's a high energy molecule, high dielectric constant, and protic solvent, you're going to go through a bimolecular pathway, so this, or unimolecular pathway. So this would be SN1E1. If you're underneath a low dielectric constant, aprotic, low temperature reaction, this doesn't occur, and so these ends up being bimolecular pathways. Now, substitution versus elimination depends on the nature of this group. If this is a base, you can promote elimination. So if we have hydroxide, this is a base. It can promote elimination. And so if you try to do hydroxide with this, you can get both elimination because it can extract a hydrogen, it is a base, and get this product, or you can get substitution. But if you do something like chloride, Cl-, chloride is not a base. It cannot possibly do the elimination reaction because it doesn't have the ability to extract hydrogen. Ethoxide is not a fun one to play with because it's not clear if it's going to do substitution elimination. In most cases, you're going to get a mixture of both. So the substitution here, the oxygen is going to attack the carbon, and you're going to end up getting an ether. Whereas if you do the elimination, it'll extract a hydrogen from down there, and you'll end up getting both the cis and trans 2 butenes. Which one does it do? Well, it does both. You're going to get both SN2 and E2. So either it's going to attack here and break the chlorine, or it's going to attack here and break the chlorine. But you can get both with ethoxide because it is big enough that it's going to have some steric strain getting in here, but it's also small enough that it can do substitution. And so again, I would say the big picture here is, one, avoid ambiguous examples. So again, in terms of picking pathways, if you're looking for a hard and fast answer, there isn't one. And the reason there isn't a hard and fast answer is like exactly with these reaction conditions, I'm going to get these, is that you're getting a blend. All these reactions occur through blended pathways, SN1, SN2, E1, E2. This is why we wait till now to do reactions instead of covering them in depth with the alkanes. It's going to be complicated. It's going to be messy. What I have found works best for predicting the reaction pathways. Whether it goes through a 2 or 1 pathway depends on the solvent. Your bimolecular pathways, these are going to be ethers. You bring them up. So, nonpolar aprotic chloroform. Dielectric constant of 4.8. Ethers, dielectric constant of 4.3. Hexane, 1.9. Methylene chloride, CH2Cl2, 4.8. Wait, no, 9.1. So these are going to promote your biomolecular pathways, and the reason they're going to promote the biomolecular pathways here is that these are awful at stabilizing carbocations. They have no dielectric constant. And because they have such a low dielectric constant here, they're not very good at stabilizing those carbocations. They are also aprotic, meaning that they don't occupy that base, so you have time for the carbocation to form. Now, that said, if you're working with a primary carbon, you're going to force this SN2 mechanism or E2 mechanism anyway, because the carbocation has to be formed, or your other option is to form a carbocation which isn't very well stabilized. Now, if you have a tertiary carbon, you may still get the one pathway despite working with these solvents, simply because it's still a stable carbocation. But these are going to be most likely to kind of get you in those positions. So, when are you likely to have a bimolecular or a unimolecular pathway? Water, dielectric constant, 78.5. Where's some good ones? Propylene carbonate. Your protic polar solvents. Formamide. $109. So these are incredibly good at stabilizing your carbocations. The other thing to keep in mind, so we look at something like formamide, it's protic. Your formic acid is protic. These polar protic solvents are going to do a really good job at stabilizing your carbocations. Now, what if you're not given a solvent? It's going to get a little ambiguous, and I wish your book would actually list the solvents and its problems. But in this case, if we want to know if it's going to be SN1 or SN2, big tip off are acids. This is usually a one pathway, because acids inherently are going to create proticness in the solvent. These acids are going to protonate some leaving group. Alcohols like secondary pathways. Your alcohols like to protonate. They like to come off. This is what's going to drive more of an SN1 pathway. Your SN2s, E2s, typically basic conditions with alkyl halides. The reason why these are going to do such a better job of not forming carbon cations is that, one, your basic conditions, it's hard to form a carbocation when you got a whole bunch of negative charges sitting around. The second is that alkyl halides aren't very good at leaving. They typically form a negatively charged ion. That negatively charged ion doesn't want to separate out from the carbocation. So for you to do an SN1 pathway with chloride, for you to break that, now you've got a positive negative charge. But if you look at an alcohol, typically what happens with alcohols is we get protonation of the alcohol first. And then that's going to break off and give you a carbocation with a neutral water molecule. So this is why your alcohols prefer the unimolecular pathways. They're easy to protonate and they're easy to pop off and you end up with a non-charged molecule. Your alkyl halides, on the other hand, much more prefer to do these types of substitutions through bimolecular pathways, because you don't generate a neutrally charged leaving group. You end up charging an anion, creating an anion which is going to want to come back. But again, I'm going to tell you this a lot, it's not black and white. You're going to have a little bit of guess and test with this. The exams are going to be very black and white because it's probably going to be a very extreme case. But again, with the homework, there was one where they had a primary alcohol that went through an SN2 pathway. It was a primary alcohol. That's what the book is calling an SN2 mechanism. But even then, the books, I have definitely sent the publisher questions because they've had situations where using the exact same reagents, they claimed an SN1 pathway in one problem and an SN2 pathway in this subsequent problem. They were literally one after the other, and they were the same reaction conditions. It is a gray area. Rely on the solvent, rely on the nature of the leaving group. If it's a halide, it's probably going through a bimolecular pathway. If it's a polar protic solvent, it's probably going through a unimolecular pathway. If it's an alcohol, it's probably going through a unimolecular pathway. So that's kind of all I can really tell you. Even me doing the homework, I'm going to occasionally get them wrong when I'm working through them because whoever wrote that problem thinks the conditions are going to favor an SN1 or SN2 or E1 and E2. Now again, I am going to go back and say substitution versus elimination, that is set by the reagent. If it is a big anionic reagent, it is probably doing elimination. If it is a small, not basic molecule, you're most likely doing substitution. So definitely your halogens, chloride, bromide, iodide, they like to substitute. Big, strong alkoxides, they really like to do elimination, but you're going to get both. But that's it for the questions I've gotten this morning. So are there any questions in the chat? What if the solar is polar, a product with a low dielectric constant? Those don't exist. You can't be polar and have a low dielectric constant. So dielectric constant shows up as an artifact of polarity. So let's look at acetic acid. Acetic acid is an acetic acid because of the strong polarity difference between the oxygen and the hydrogen. And this ends up being a very polar molecule. Oops, wrong way. Because of all the electronegativity differences. The reason why this ends up being protic is because oxygen and hydrogen represent an extreme case of polarity. Oxygen is super electronegative, hydrogen is not. Oxygen is the second most electronegative element of the periodic table. It's going to dissociate. So in order for you to have a protic solvent, you have to have a massive disparity between two electronegativities. But the thing is, this positive negative charge is what's stabilizing your carbocation. So if you have a carbocation, what's happening is that this oxygen here has a negative charge, and there's an affinity for that carbocation. Now, this oxygen is occupied in its bonding, so it can't form a bond with the carbon. But this negative charge attaches to this positive charge, and you still got a positive charge on the hydrogen here, but it's not a true +1. It's kind of like between a 0 and a 1. And so instead of seeing, if you're sitting here looking at molecule, you're not seeing this +1 charge anymore. What you're seeing is the slightly less +1 charge from this hydrogen. And if we have another carboxylic acid group, that's also going to shield you from that positive charge. And so the way a dielectric constant works is that you have we'll get to that in a minute. So what happens with dielectric constants is you have something that's very good at generating charges or looking like it has charges, and that's how it shields charges. Oh, I'm sorry, I thought you said polar protic. Now, polar aprotic with a low dielectric constant, that's not going to do. So this is where we get into polarity as a spectrum as well. So, sorry, what I thought you said was, is it possible to have a polar product solvent with a low dielectric constant? The answer is no. That's impossible because in order for it to be protic, it has to have high polarity. Now, can you have a polar aprotic solvent with a low dielectric constant? Yes, because polarity is not. Polarity is a spectrum as well. So we've got three molecules here: trichloromethane, dichloromethane, monochloromethane. All three of these are possible. All three of these are polar, but the question is, are they equally polar? And the answer is no. This is actually less polar than this. And the reason that this is less polar is that you've kind of got three big chlorine groups and this tiny hydrogen. So yes, this is positive and this is negative, but because they take up so much space, they end up basically looking like one big charge. Whereas here you have a big chlorine atom and three little hydrogen atoms. And so it makes it a little bit easier to kind of see this dipole, that you got the negative here and the positive here versus here where it's pretty much a big chunk of negative with a little bit of hydrogen positive sticking out. So again, all three of these are polar molecules. This just looks more polar than the trichloro because of how the charges are arranged in space. So this is where the dielectric constants start showing up, is to say that, well, if you looked at their respective dielectric constants, this would have a higher dielectric constant than this. So this is more likely to drive your unimolecular pathways. This is less likely to do it. But polarity, unfortunately, is taught as this bipolar notion or dichotomous notion. You're either polar or you're nonpolar. The thing is that there are definitely polar molecules that act nonpolar. This is soluble in hexanes, even though this is polar, and this isn't soluble in water. So the trichloromethane is used, actually the methylene chloride is a good example of this. Methylene chloride is used a lot in organic chemistry because it acts like a nonpolar molecule, even though it's listed as polar. And it's actually so nonpolar that it will not dissolve in water, but it will dissolve polar organic compounds that aren't soluble in water. So yes, it is possible to have a polar aprotic solvent with a low dielectric constant, because the only thing polarity says is that there is a charge difference between ends of the molecule, or there's a part of the molecule which has a charge difference. But polarity makes no statement about how large that charge difference is. Your dielectric constant does. If you have a large dielectric constant here, and when we say large, we're saying on the order of water, that is something that likes to stabilize charges. But if you get a low dielectric constant with something like methylene chloride, which is so nonpolar, I mean, it's listed as polar, but it's so nonpolar it doesn't dissolve in water, that's when you're actually kind of getting to the nonpolar end of the spectrum. All right, so with the time that remains, second problem on the solvent effects reactions. So we have HCl and DMSO versus HCl. So we have our DMSO here, 48.9 polar protic, and then we have our tetrahydrofuran, THF, which is 7.6. So this is polar aprotic, but we're seeing radical disparities here in terms of what would be considered as good dielectric constant. So DMSO here versus THF. So THF has a dielectric constant of 7.6, and DMSO here has a dielectric constant of 48.9. These are both listed as polar aprotic. The question is, do they actually act differently? Well, if we look at something like water, and we've got it on here. So look at water versus methanol. So water here sits at 78.5, and your methanol sits at 32.6. Okay, both of these have pretty high dielectric constants, and DMSO sits between the two of them. So I'm going to say that DMSO here is going to act kind of like water and methanol. It has a very good ability to stabilize charges. Whereas if we look at, where are you? Tetrahydrofuran, okay, it's in the single digits. And I think dielectric constant for acetic acid is wrong on this table. We look at things that we know are bad at stabilizing charges. Chloroform. Chloroform here sits at 4.3. Hexanes. Sit in a range of 1.9. So our ubiquitous nonpolar, not going to stabilize the charge at all here, are all sitting at like 4 and 1. This isn't too far off, but it's definitely radically off from water. So this is a good charge stabilizer. You're probably promoting the unimolecular pathway. Something like THF, this is going to promote the bimolecular pathway because it's not very good at stabilizing charges. So for the second problem on solvent effective reactions, your THF here, you're probably going through the SN2 pathway. And what you're going to end up producing when you get done with the SN2 pathway is a majority of this. Now, you've also got HCl. So what do you expect to happen? You may also get some rearrangement as well. So yes, you will get some of the SN1 pathway, but here the SN2 pathway is going to be the major product for the THF. When we go up to DMSO, we expect these to flip. We expect the SN1 here to be the major product and the SN2 pathway to be the minor product. Now, this is a primary alcohol. Is it going to want to favor an SN1 pathway? No. But the thing is that even though the SN2 pathway may be the more favorable pathway, it's super slow. And because we've stabilized our SN1 pathway, we're probably going to drive that reaction more. So that's it for the live stream today. If you got questions, I've got another live stream tomorrow at 11 o'clock. So feel free to ask questions then. And I will see you all tomorrow.